vocabulary words that we're going to hit today. I would encourage you to go ahead and write these down and kind of skip a few lines in between them. We're going to take about 2 to 3 minutes in order for you to do that. During that time, it is also reasonable for you to download the app Desmos. You can get Desmos in any app store. www.desmos is also a good source. So take about 3 minutes, write down these vocabulary words, and download the app Desmos. Can I move off the screen? Okay, so these are vocabulary words you're going to want to kind of be listening for today. The first we're going to talk about is the domain and range of a function. You have heard a lot about your x values and your y values. Domain is associated with my x value. It's also associated with my input. In science and in statistics, you might also hear that called independent variable. Okay? So anytime we're talking about the domain, we're talking about the x value, the input, the independent variable. The values that are on the horizontal axis. So when I'm talking about domain, you're looking at the horizontal axis, which is the x-axis. When I'm talking about range, I'm talking about the y value. Remember that y and f of x are interchangeable. I'm talking about the output or the dependent variable. Now in math, we don't use independent and dependent variable nearly as much as it's used in science and then statistics. Okay? But I do want you to associate that definition with the domain and the range. Students typically remember domain and range. Sometimes they don't remember how to do interval notation. And we are going to write several things in interval notation today. Very often a solution to something will be all real numbers. all real numbers. The way that we write all real numbers in interval notation is negative infinity to infinity. That means every single value of x is included in all real numbers, negative infinity to infinity. Now, if you remember from, I was going to say preschool, it's definitely not preschool, middle school, when you were graphing on a number line, sometimes you would use an open circle and sometimes you would use a closed circle. It would be an open dot or a closed dot. Okay? The parenthesis is similar to the open dot. That means that the number is not included. So look at this right here. I've got x is greater than 3. X is greater than 3. Is 3 a solution to x is greater than 3? No, it's not. Is 3.001 a solution to x is greater than 3? Yes, but 3 is not included. So when I am not including the number, I am going to have a parenthesis right there. When I've got a value such as x is greater than or equal to 3, 3 is a solution. And the way I show that is by a bracket. I show the bracket right there. So that is interval notation. That's what we use when we're talking about domain and range. Okay? And we're going to use that a lot more today. But any general questions on that? Okay. I see a couple of people writing. Can I move off this slide? Okay. We are going to find the domain of this function right here. So this function is f of x equals x squared plus 3x plus 2. Okay? And if we look at this portion of my quadratic goes all the way. It keeps going and keeps going and keeps going. So it's going to get all the way to positive infinity. This portion of my quadratic is going to keep going and going and going. And we're looking at the x-axis, and it's going to keep going to negative infinity. So my domain of this, and I'm looking at the values on my x. Okay? I'm not looking at the values on my y. To look at the values on my y, you'd be dealing with range. But right now I'm asking for the domain of this particular problem. And the domain of this particular problem is negative infinity to positive infinity. And that is because I am looking at the x values. And my parabola keeps getting wider and wider as my x values get bigger or my x values get smaller. So the domain for all parabolas is always going to be negative infinity to infinity. There are 2 times for the purposes of this class that you have to limit your domain. You have to limit your domain when your variable is in the denominator, and you have to limit your domain when the variable is in the square root. That's when you limit your domain. When I've got x squared plus 3x plus 2, I do not have the variable in the denominator, and I do not have the variable inside the square root sign. So when neither of these is happening, neither one, my domain is all real numbers, which is negative infinity to infinity. Okay? Now, for the next one, I want you to pull out your calculator and I want you to divide by 0. And you can do that on your phone, calculator, or whatever. You can divide. I want you to see what happens when you try to divide by 0. What happens when you try to divide by 0? It's error. Okay? We can't divide by 0. Anything divided by 0 is undefined. It's like when we do the slope of a line. The slope of the line is undefined when we get 0 in the denominator. So for this particular function right here, if I look closely to this line, you will find that my function approaches that line, but it will never cross it. My function approaches this line right here, but it will never cross it. This is a situation where we cannot have 0 in the denominator. It's okay if x equals 0. What can't happen is whatever is in the denominator of this function can't be 0. So when I have a variable in the denominator, and that is one of my 2 conditions that we look for, variable in the denominator, what I'm going to do is I'm going to set my denominator equal to 0. I don't care anything about the numerator. Okay, in this situation, my numerator is 1. But it doesn't matter what it is. Okay, I don't care about that. I'm only worried about the denominator. And whatever values of x make that 0, that's what x cannot be. So in this situation, 3 minus x cannot be 0. So I've got to determine what values of x make my denominator 0. So all I do is I take my denominator, set it equal to 0, and that's what x cannot be. So I'm going to solve this. The first thing I'm going to do is I am going to subtract 3 from both sides. So I'm subtracting 3 from both sides. Then I have negative x cannot be negative 3. I divide by negative 1. And I have that x cannot be positive 3. And that correlates right where that vertical line is. Do you see my vertical line highlighted in pink? That's x equals 3. My graph will never ever touch that line. It will approach it, but it will never touch it. And that's x cannot be 3. Now I want to write that x cannot be 3 in interval notation. So we are focusing on the values of the x-axis. And that means that my x value can be anything here, any of these values, and it can be any of these values. It just can't be that particular value right there. So what starts all the way to the left? What value is all the way to the left? Negative infinity. So now I am writing this in interval notation. So I start at negative infinity, and I'm going all the way to what number, but I'm not including that number? 3. Okay, I'm not including 3, so I put a parenthesis. Then this means union. Union means or. Okay? Then I start again. I don't include 3, but I start at 3, and I go all the way to what? Positive infinity. Okay? So that right there is how we write that in interval notation. Negative infinity to 3, union 3 to infinity. Okay, can I go to the next one? Okay. What I want you to do now is I want you to take the square root of 0. So I want us to determine if I'm allowed to take the square root of 0. So on your calculator, take the square root of 0. Yes, what do I get? What's the square root of 0? 0. Okay, the square root of 0 is 0. Okay, so it is something that is allowed. Now I want you to take the square root of negative 4. The negative 4 is going to be inside the square root sign. What does it say? Error. Okay, we cannot have a negative number inside a square root sign. And when we think about this, it makes sense. We think, okay, that makes sense. I can't have a negative number inside the square root. But we always forget. We remember that the denominator can't equal 0, but we forget about this one. So what students do is they take that x minus 16 and set it equal to 0. And then they miss the problem because they're not thinking about the rules for square root. So it's two distinct things. Okay, here we cannot have a negative number inside the square root. That is what we cannot have. Okay, cannot have a negative inside the square root. Is 0 okay inside the square root? Yes, 0 inside the square root is completely fine. I just can't have a negative. So what I'm going to do is I am going to take what's inside the square root, x minus 16, and I have to put that as greater than or equal to 0. It's okay for x minus 16 to be 0. It's okay for x minus 16 to be greater than 0. X minus 16 just can't be less than 0. So the domain for this one, once I solve this, I'm going to have x is greater than or equal to positive 16. So for this domain, I am looking at these values right here. So how do I write that in interval notation?
16 to -4 to infinity.
Good, good. So it's going to be 16 to infinity. Am I going to have a bracket or am I going to have a parentheses? Bracket. Why? Because 16 is included. Now, students always want to know, well, Alicia, if it's greater than or equal to, why do I not have a bracket right here? Okay? You definitely have a bracket right here. Why don't I have a bracket right there? The reason is infinity is a concept. Okay? Infinity is a concept, and there can always be one more number. Do we ever get to infinity? No, we never ever get there. So that's why we always have the parentheses around infinity. Now, just for fun, because this one makes it kind of easy for us to look at, I want us to determine the range of this one. Now, for our domain, we have been looking at our x. For our range, we are going to be looking at our y. Okay? So we are going to look for our y values. Now, this particular graph, it gets higher and higher. So as I continue towards infinity on my x value, what am I continuing towards on my y value? Infinity. And remember, it goes on forever. Now, do I have any y values down here? No, I don't. Okay? So I'm going to focus on this point right here. Because I'm focusing on domain, when I'm focused on domain, I'm focused on my x value. When I am focused on my range, what am I focused on? Y value. So this point right here is 16, 0. So for my range, I'm going to look at that 0. That's where my range starts. So what do I have? 0 to infinity. Okay? Because it keeps going. It keeps going. It keeps getting higher and higher and higher. Okay? There's nothing that's going to stop it. Okay? Can I move off the screen? Good? Can I move off the screen? Okay. Now, who can remember what kind of function this is right here? Does anybody remember? Piecewise, okay? We did piecewise last Tuesday, or Thursday, I'm not sure which one. And this is the graph of a piecewise. And if you'll remember, when we're talking about piecewise functions, we follow the rule based on what input we put in. So So in this particular situation, if I put a negative number in, the rule that I'm going to follow is t plus 1. Okay? If I put in a number between 0 and 2, or if I put in 0, or if I put in 2, I'm going to follow the f of t equals 1, which is the horizontal line. If I put in a number greater than 2, negative t plus 3 is what I'm going to follow. Now, try not to let the t confuse you. What can I think of the t as? Can I think of the t as an x? Yes, I can. Okay? So don't let that confuse you a great deal. Okay? So I'm still talking about domain and range based on input and output. In this situation, my input happens to be t. Okay? So, what is the domain of this function? And I'm going to go ahead and add arrows right here so that you know it keeps going forever. So domain is my x value, or in this situation right here, it's my t. So t and x in this situation can be interchangeable. What is my domain for this graph? Negative infinity to positive infinity. Okay? Negative infinity to positive infinity. Now, I want you to look at my range. My range is going to be the values on the y-axis. Okay? Now, these are going to go on forever. So, where does my y values start? Negative infinity. How far do my y values go? To positive 1. When I am dealing with my range, you are focused on the y values. So my range for this is negative infinity to positive 1. Is positive 1 included or not included? It's included. Okay. Now, I want us to talk about increasing, decreasing, and constant intervals. Increasing, decreasing, and constant. Can I erase my domain and range information? Can I erase that? Okay. So now, we are looking at increasing. That is when my x value is increasing. Then I want to know, where is my x value decreasing? And when is my graph constant? So let me say that more appropriately. Okay? Where is my graph traveling in a positive slope? Good. Okay? And where is my graph traveling in a negative slope? And that, yeah, you're right. Okay? So here is where my graph is increasing. Okay? Because I had said, where is my x value increasing? And I should not have said that, because as we move from this end of the graph to the other end, our x value is always increasing. So what I want to know is, when does my graph appear to have a positive slope? Where does my graph appear to have a negative slope? So that's a better way for me to say it. So my graph is increasing. I am increasing here. Okay? That is where my graph is increasing. Now, when I write interval notation for increasing intervals, I always use parentheses. Because at 0, 1 and at 2, 1, what's happening is I'm changing directions. My graph is changing directions. So I'm not going to include that point in my increasing and my decreasing. That typically confuses students because they want to include that point. Okay? But you don't have to, because what's happening at that point is I'm changing directions. So in this situation right here, I am increasing from negative infinity to 0, because remember, I am focused on those x values when I'm talking about domain and when I'm talking about increasing, decreasing, and constant. I want to know my x values. When do I worry about my y values? For range. Good. Okay? So I am increasing. What is happening here? What is happening right here? It is constant. Okay? So between 0 and 2, because I am focused on those x values, my graph is constant. What is happening here? What's going on here? It's decreasing. Okay? It's decreasing. Okay? So I start at 2 for decreasing, and where do I go? Infinity. Okay? So these are increasing, decreasing, and constant. Okay? Can I go to the next screen? Okay. What I want to talk about now is I want to talk about relative maximum and relative minimum. You have looked at quadratics before, and you've seen a graph of a quadratic quite a bit. A quadratic has what we call is a vertex. A vertex. That vertex is going to have a maximum value or it's going to have a minimum value. Okay? You're only going to have a max or a min when you're talking about a quadratic. If we are talking about something that's cubic or quartic or a piecewise function or something like that, we can have more than one. We can have a relative maximum or we could have or a relative minimum. This is a cubic function, and we'll do lots and lots of stuff with cubic functions as we move towards chapter 3. But this cubic function has a relative maximum and a relative minimum. Now, this goes all the way to negative infinity, and that goes all the way to positive infinity. On my x-axis and on my y-axis, we're going to have negative infinity and positive infinity. My relative maximum and my relative minimum, the key to something being that is we are looking for a change in direction. That's what happens with the graph. When I hit a relative maximum or a relative minimum, I have a change in direction in my graph. Okay? So my relative maximum, my graph changes direction right here. So this point, negative 1, 2, that's my relative maximum. What's my relative minimum? The other one, 1, negative 2. Okay? What is the domain of this graph? What's the domain? Good. It's all real. Negative infinity to positive infinity. Okay? What about the range? It's the same. All reals. Negative infinity to positive infinity. Okay? Now, so the big thing about this slide is your relative maximum and your relative minimum is a change in direction. Change in direction. Okay, can I erase this? Yes? Okay. What I want you to do now is I want you to determine intervals. So I want you to determine where is this graph increasing, where is this graph decreasing, and where is this graph constant. I'm going to give you about 60 seconds to determine that. Okay? Now remember, for intervals, you're only going to use your parentheses. You're not going to use brackets. Okay. So where is my graph increasing? So it has what we think of as a positive slope. Who wants to raise your hand and tell me?
From negative infinity to negative 1, and then from 1 to 0.
Good. Good. Both of those intervals have an increasing. So I am looking at, anytime I'm talking about intervals, I want to know the values of the x-axis. Okay? So I am looking at these values. I'm looking at the direction of the graph to determine what's increasing, decreasing, or constant. But the values that I put for my interval notation are the x values. So that negative 1, 2, when I'm talking about my increasing interval right there, what I'm focused on is the negative 1 because it's the x value. So here, I write my increasing is negative infinity to negative 1. Then my second part of the graph that's increasing is positive 1 to positive infinity. Because I'm looking at these x values right here. Okay? Now, the part of my graph that's decreasing is this portion right here. Who can tell me what that is in interval notation? Yes, negative 1 to 1, because we are looking at our x values, negative 1 to 1. Now, does this graph have a constant? No. Our other one did because we had a horizontal line. This one doesn't, and sometimes you don't. Okay? Good. Good job. And you can write none. You can write none under constant if you want to. Okay? Now, can I move off this slide? Okay. Now, I want to direct your attention to the board up here where I've got my x-axis, my y-axis, and my origin. We did this last week. We talked about symmetry to the x-axis, symmetry to the y-axis, and symmetry to the origin. So it's not a terrible idea to take a picture of this up here because I've added a few things to it. My first one, I am trying to determine if something is symmetrical to the x-axis. When I determine if something is symmetrical to the x-axis, if I'm looking at the graph, that means I fold the graph. I fold the graph on the x-axis. If it's on top of each other, then it's a function. I'm sorry. If I fold it and it's on top of each other, then it's symmetrical to the x-axis. Okay? That's how I look at it graphically. If I look at it algebraically, what I do is I replace y with negative y. Okay? I replace y with negative y. If I get my original function, then it's symmetrical. This is symmetry with regard to the x-axis. In this right here, I want to know if something is symmetrical to the y-axis. The way I determine if something is symmetrical to the y-axis is I look at it, and if I can fold it along the y-axis and it's on top of each other, then it is symmetrical. That's how I look at it graphically. If I want to do it algebraically, and you will be required to do it algebraically, what you do is you replace x with negative x, simplify it, and if you get your original function, then it is symmetrical with regards to the y-axis. Our last one is in regards to the origin. Something is symmetrical to the origin if you look at the graph, you fold it along the y-axis and you fold it along the x-axis, and it's on top of each other. That is symmetrical across the origin. The way you determine that algebraically, you replace x with negative x and y with negative y. If you end up with the same function, then it's symmetrical. Now, we are going to take this knowledge right here and we are going to apply it to even and odd functions. So something is an even function if it's symmetrical to the y-axis. Something is an odd function if it's symmetrical to the origin. Now, we've left out something being symmetrical to the x-axis. And the reason that we've left this out is it does not pass the vertical line test. If it does not pass the vertical line test, what's it not? It's not a function. Okay? So the reason that symmetry to the x-axis does not have a special name is because we aren't even dealing with the function. So we throw this out completely. So when we talk about even functions and odd functions, we are only talking about symmetry to the y-axis and symmetry to the origin. Because when we talk about symmetry to the x-axis, if something's symmetrical to the x-axis, then it cannot be a function. Nothing that is symmetrical to the x-axis is a function. So we only have even and odd functions. Now, what you need to know about even and odd functions. It's always a good idea to look at the graph. But I'm not asking you to tell me if something's an even or odd function based on the graph. Does the graph help you? Yes. Is that what I'm asking you to do? No. I am asking you to show me algebraically. However, when you look at the graph, you will have a good idea on whether or not it's symmetrical or not. What I want you to realize is, when we are dealing with even functions, you only have to test to see if something is an even function if its highest exponent is even. If its highest exponent is not even, you don't need to test to see if it's an even function. If its highest exponent is odd, it automatically is not an even function. It may not be an odd function, but it's definitely not an even function. You only need to test something to be an odd function if its highest exponent is odd. So, every student that's a student at Montevallo comes to campus. Okay? I know there's a few online classes, but every student that's a student at Montevallo has to come to campus. Would you agree with me on that? Yes, every student that's a student at Montevallo has to come to campus. Would you agree that every person on the Montevallo campus is a student? No. Okay? So because I say every student that's a student at Montevallo has to come to campus, because that's true, it doesn't mean the opposite of that is true. It doesn't mean that every person that's on campus is a student. So what you need to think about here, and what you need to hear me say, to be an even function, it has to have an even exponent. Okay? All even functions must have the highest exponent being even. However, just because it is an even exponent doesn't make it an even function. Okay? So I'm going to show you what I mean by that using odd functions. So I want us to look at this function right here. Okay? This function is f of x equals x to the third minus x. Okay? So I have f of x equals x to the third minus x. So my highest exponent here is 3. Is 3 even or odd? Odd. Okay? That automatically means it's not an even function. Okay? I don't even need to test to see if it's an even function because its highest exponent is odd. Okay? the only test I need to do on this is symmetrical to the origin. So f of x equals x to the third minus x is the same thing as y equals x to the third minus x. To test if something is symmetrical to the origin, I replace y with negative y. Then I replace x with negative x. Okay? What value is in front of those x's? Negative 1. Okay? So let's look at that. I'm going to leave my negative y as negative y. Negative 1 to the third power is what? Negative. Negative 1 times negative 1 times negative 1 is going to leave me with negative 1. Then I still have x to the third power. My second, then I've got minus negative 1x. That's to the first power, so I leave that the same. But I do have to eliminate this double negative, right? Okay, so I have negative y equals negative 1x to the third plus x. My next step is to divide everything by negative 1. So then I'm left with positive 1x to the third plus x. Do I have to have that positive 1 written down? Okay. Is this the same as this? Well, no. Where did I mess up? Oh, I see where I messed up. Yeah, okay. Okay. Negative 1x to the third divided by negative 1 is 1. Positive x divided by negative 1 is negative x. So that is the same. Okay? There we've got it. So x to the third minus x and x to the third minus x are equal. That means that this function is symmetrical to the origin. If I fold it on the y-axis and I fold it on the x-axis, am I good? Yes. This is an odd function. This odd function has an odd exponent. Because it has an odd exponent, I have to test to see if it's an odd function, but it doesn't automatically make it an odd function. Okay? So this is a situation where I do have an odd exponent and it is an odd function. I want you to look at this one. X to the third minus 1. So this is f of x equals x to the third minus 1. You should be able to tell by looking at this whether or not this is an odd function. Is it symmetrical to the origin? No. Can I fold the y-axis and the x-axis and this be on top of each other? No. Okay? So this is not symmetrical to the origin. It does have an odd exponent. So do I need to test for symmetry to the y-axis? Okay, symmetry to the y-axis is what kind of function? Even or odd? Even. This has an odd exponent, so do I need to test for that? No, I only need to test to see if it's an odd function. So even though looking at this graph, I'm like, nope, that's not going to be an odd function because it's not symmetrical to the origin, I still have to show that algebraically. And this is how I show it algebraically. I take y equals x to the third minus 1. I replace y with negative y. I replace x with negative x. Okay? What is negative 1x to the third power? Negative x to the third power. Okay. My next step is to divide everything by negative 1. So I get x to the third plus 1. Is that the same thing? No. This is not an odd function. Even though it's got an odd exponent, it's not an odd function. Okay? Do you see the difference with that? Okay, so the answer to this one is not odd. We know it's not even. How do we know it's not even? It doesn't have an even exponent, so we know it's not even. Okay? This one is an odd function. Okay? Now I want us to look at this. This function is f of x equals x squared plus 1. What do I only need to test for? Even. I only have to test for even. The reason that I only have to test for even is because my highest exponent is even. It automatically is not an odd function. Okay? So the way that I test for an even is I replace x with negative x. What is negative x squared? Good. It's positive x squared. Okay, because negative 1 times negative 1 is positive. Is that the same thing? Yes. That means this is an even function. So I have algebraically shown that this is an even function. Okay? This is one of those topics that students typically have trouble with. So kind of focus on that and think about that. So the answer to this one would be even. This is an even function. Okay. Can I go to the next screen? Okay, our next vocab word that we're going to talk about is we are going to talk about roots. Roots of a function. Okay? Roots of a function. So this function right here is f of x equals 3x minus 15. And I am being asked to find the root of this function. And this particular function only has one root. Okay? You have done this before. It's just probably not been called roots before. Roots is not something that all books call it. Roots can be called a solution to a function. It can be called a zero of a function. It's also where the x-intercepts of a function are. Okay, now this is linear. And any time that we talk about something that's linear, we're almost always focused on the y-intercept. But you can have a zero of a linear function. The zero, or the solution, or the root of a linear function is where it crosses the x-axis. So when you are asked for the roots, what you are being asked for is where the graph crosses the x-axis. That's what I'm being asked for. All of these are interchangeable. And the way that we do this is we set function equal to 0. That's how we solve this. So I've got 0 equals 3x minus 15. I add 15 to both sides. So I have 15 okay, 15 equals 3x, and I divide both sides by 3. Okay? So 5 equals x. What's my y value here? 0. Okay? So x equals 5, or 5 is my root in this situation. I have set this equal to 0. That's what I've done. So in a linear function, we're looking for the x-intercept. We plug 0 in for y. Now we can do this for any type of function. We can do it for any type of function. Here, I have a quadratic. This is f of x equals 3x squared plus x minus 10. I want to find this value, and I want to find this value. Now, one of the values is negative 2. I can see that pretty clearly. The other value is approaching 2, but it's not 2 yet. It's somewhere between 1 and 2. So I can't tell by this graph. So I need to set this equal to 0, and I'm showing it algebraically. So I have 0 equals 3x squared plus x minus 10. What do I have to do in order to solve that? Say that again. Good. That is if it was linear. Okay, think about what I do when I've got something squared. It's that F word everybody hates. Factor. FOIL is way better than factor. Do you remember factoring? Okay. So in order to do this, I am going to take the 3 and I am going to multiply by the negative 10. What's 3 times negative 10? Negative 30. Okay, so my product that I'm looking for is negative 30. What's my sum? Positive 1. It's what's in front of the x. Good. I heard several people say it. Good job. What are my two numbers? Good. And the reason my two numbers are positive 6 and negative 5 is 6 times negative 5 gives me negative 30. 6 plus negative 5 gives me positive 1. Those are my two numbers. Now, I know factoring is not something that we love. I know factoring is not something that we have mastered. As we approach chapter 3, it will become more of something that you want to pay attention to. Okay? So, now at this point, I have 3x squared plus 6x minus 5x minus 10. 3x comes out of both of these. Okay. What do I have to take out of my second set of numbers? Negative 5. Excellent. Good. So my factors are 3x minus 5 and 3x plus 2. So then I set each one of those equal to 0. So this is where I get my negative 2 from. Okay? That is this root right here. 3x minus 5 equals 0. I get 3x equals 5. I divide both sides by 3. And I get 5 over 3. So my roots are 5 over 3 and negative 2. It's where my graph crosses the x-axis. It's the x value when I cross the x-axis. What's my y value when I cross the x-axis? 0. Okay? Now, that one was difficult because of the factoring. Okay? We just kind of have forgotten how to factor. This one looks difficult, but it's really not. It's really not as difficult as it looks. Here I've got f of x equals the square root of 10 minus x squared. F of x equals the square root of 10 minus x squared. The roots of this we can see right here. Okay? It's somewhere between 2 and 4, and it's somewhere between negative 2 and negative 4. I'm going to solve this the same way. Okay, I'm going to set this equal to 0. And I know you might be thinking, oh, I don't know how to do that, Alicia. But you do. You do. Okay? What's the inverse or the opposite of a square root? Squaring. Okay, so what I'm going to do here is I am going to square both sides. I'm going to square 0 and I'm going to square this. When I square 0, I just get 0. What happens when I square the square root of 10 minus x squared? The square root's gone. So I'm just left with what's inside. So now I have 0 equals 10 minus x squared. And you know how to solve this. I'm going to pull the 10 to the other side. So I've got negative 10. Negative 10 equals negative x squared. Okay? So x squared is 10. Now, before I do anything else, if I told you x squared equaled 4, you immediately could tell me one of those values. What's one of the values of x squared equals 4? 2, because 2 squared is 4. Is there another value? Negative 2. So when we take the square root, we've got to account for the positive and the negative of it. Okay? We've got to account for the positive and the negative of it. So when I take the square root of 10 to find out what my x is, what do I have to put in front of it? Plus or minus. Okay? So here, this is minus the square root of 10, and this is plus the square root of 10. That's where my graph hits the x-axis. Okay? Okay. And the next one looks intimidating, but it's not, I promise. Okay? Here I have f of x equals 2x minus 3 over x plus 5. 2x minus 3 equals x plus 5. I'm going to set this equal to 0. Okay? If I had x over 5 equals 0, and this is, I'm up here in this right-hand corner, 0 equals x over 5, what would I do to solve for x? Absolutely, that's exactly what I would do. I would multiply by 5 on both sides. I would multiply by my denominator. What's my denominator here? Excellent. So I am going to multiply by x plus 5 over 1 on both sides. Okay? Therefore, I end up with 0 equals, those cancel, just like it did with my 5, 2x minus 3. And can I solve 0 equals 2x minus 3? Okay, so the x plus 5 right here. Okay, it is multiplied times 0, so it's 0. But that's a great question. Okay, and these cancel out just like our 5 did. But yeah, because it's if it wasn't multiplied by 0, we'd have to distribute and multiply it out. A good question. Okay, so now I can solve this, right? So I add 3 to both sides. So I have 3 equals 2x. Divide by 2. So 3 over 2 is my root or my solution. And if I look right there, that is 1.5. 3 over 2 is the same thing as 1.5. And that's where I'm crossing right here. Okay? So I got to notice that my iPad is about to run out of batteries. Just because today hasn't been a fun enough technology day, my iPad's about to run out of batteries. And then it's quit recording, but I did catch it, and so I started recording again. So I do have one more thing I want us to do before we go. Could I move off the screen? Okay. Now, on 2.6, numbers 17 through 23, and you're only doing the odd. So you're doing 17 through 23 odd. The directions say, what are the values of x when f of x is set equal to g of x? And then it says, where do the graphs cross? So I'm telling you all that to tell you what you need to do is to set the functions equal to each other. That's what you're doing, is you're setting the functions equal to each other. So on 2.6, your homework 2.6, on numbers 17 through 23, what you're doing is you're setting the two functions together. And what we are trying to determine is where do these two functions cross each other. And I'm going to show you what that looks like, but we're going to do it algebraically first. So I'm going to take this function, x squared minus x plus 6, and I'm going to set it equal to this function. Okay, so what I'm doing is I am setting the functions equal to each other. And that's different than what we have been doing. So the directions are saying, where do these functions cross? That's what it's wanting to know. Is where do they cross? And so what we're doing is we're setting them equal to each other. And when we do that, we determine where they cross. Now, x squared minus x plus 6 equals negative 4x plus 60. So what I want to do now is what? Well, and that's what we would do if it was linear. You're absolutely correct. If it was linear, that's what we would do. Because it's a quadratic, that means it's raised to the second power, I have to set it equal to what? 0. So now I'm going to set it equal to 0. Okay? So I'm going to add 4x to both sides. So I have x squared plus 3x plus 6 equals 60. Now I'm going to subtract 60 from both sides. So I have x squared plus 3x minus 54. Okay? Yes. Yes. That's exactly what we would do is factor here. Unfortunately, because this is 1 right here, it's a little bit more straightforward to factor. So we're looking for two numbers multiplied together give me negative 54, and added together give me 3. Because my product is negative, what can you tell me about the two numbers?
One is positive, one is negative.
One's positive and one's negative. Okay? Has anybody got the numbers? Positive 9 and negative 6, and you are correct. Okay? She got that because 9 times negative 6 is negative 54. 9 times negative 6 is negative 54. 9 plus negative 6 is 3. When I set each one of those equal to 0, I have x plus 9 equals 0 and x minus 6 equals 0. My x values are negative 9 and positive 6. So when my x value is negative 9, these two functions are crossing. I'm not talking about the x-axis. I'm talking about their relationship with each other. When my x value is 6, they are also crossing. Okay? So let's look at it. Here's my function. So what do I have? Negative 9 and positive 6? Okay. Here is where the two cross. Got one right here. Got one right here. Okay? Each one of these is 5. So I have 5, 10, 15, 20. So just past 5 is 6. Right? Okay? So my function is crossing here when x equals 6. The other one, 5, negative 10, I'm just shy of negative 10, and that's where my function crosses. So what I have found is, I have found my x value where my functions cross. That's what I found. The x value where my functions cross each other. Okay, I'm not looking at the x-axis here. I'm talking about each other. Okay? So, quiz 0 is due on Friday. If you come to the help session today at 1, I'll have copies. No office hours on Wednesday. I won't be on campus. I do have additional office hours on Thursday. Quiz chapter 2 is on Thursday in class.